Hi there! This video series is to display my problem-solving and learning abilities. I plan to show that I can quickly solve any programming problem, regardless of whether I already have expertise in a particular language. I hope this helps others in my field to learn not just how to solve one problem, but how to teach themselves a solution to an unfamiliar problem. For now, I am learning Python. I have no professional experience or formal training in the language, and have only been learning it since mid-January. While I'm picking it up fairly quickly, I cannot claim any real expertise. Today, I'm showing my approach to solving the 12th Project Euler problem, which I have not even read yet, talking through my thought process as we go. As always, I will link to both Project Euler and my repository in the description. Let's dive in. Highly divisible triangular number. The sequence of triangular numbers is generated by adding the natural numbers. So the 7th triangle number would be 1 plus 2 plus 3 plus 4 plus 5 plus 6 equals 28. The first 10 terms would be 1, 3, 6, 10, 15, etc. Let us list the factors of the first 7 triangle numbers. So 1, 3, 6. Okay, so I'm not sure why they're calling them triangle numbers, but it's just the sum of the sequence. So then it is showing the factors. And we can see that 28 is the first triangle number to have over 5 divisors. What is the value of the first triangle number to have over 500 divisors? Okay, so first thought is, I don't think I quite understand the problem. So if 1 is a triangle number because it's 1, and 3 is a triangle number because it's 1 plus 2. Okay, I see now. So 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5. Okay. So, first triangle number to have over 500 divisors. So, we want to find a very large triangle number. Such that it is divisible by 501 numbers. So, first thought is it looks like we have to bring back our is a factor method. Maybe refine it a little bit for this exact situation. And then also yeah, so there's 2 challenges here. One is counting the number of divisors, and the other is finding the triangle number. And the simplistic approach, of course, is to just sort of count, right? Calculate, okay, we know that 28 is the 7th. Maybe even start there, just save ourselves a few steps, calculate the triangle number, find all of its divisors, count them. I think when we're looking for 500 divisors, there's no way to write that simplistic approach in a way that is at all efficient. So it's probably smarter to kind of look for a pattern here. And I would say it's a little bit difficult to find that pattern. So what do we want to do first? I think that first we're going to have to figure out how to count how many divisors a number has. And perhaps... So, like, maybe we just start with that simplistic approach that I already know won't be efficient enough, probably. Like, there's no way, right? Like, I don't think it is possible for it to be efficient enough. But let's go ahead and get started. Problem 12.py. I forgot to copy. First triangle number to have over 500 divisors. So, I would say that for purposes of what we're doing, a number likely has fewer divisors than its place in this sequence. So we can see, well, except for the case of 1, 3 is only divisible by 1 and 3, 6 is divisible by 4. Oh, but it's already the third one. Okay, so that's not quite it. We can't guess at the number of divisors based on the size of the number. But let's see. Let's start with 1. Actually, let's start with going and finding this part so that we know how quickly our algorithm runs. Not much use in being like, this is inefficient. We want to know how inefficient. Okay, first triangle number. So we probably will need some sort of a sum variable. Let's go find that is factor method. Here we go. Not that we can't rewrite it or anything, it's just sort of easier. And we maybe want to create a count factors definition. Let's work on that. Let's say count factors of num. Okay, typing is still a little painful with my wrist injury. And we want to have a count equal to 0, and we're going to return count and then basically for, let's say, n in range, num, the square root of num, which I believe is num. Go back and going back to problem 7 to look at our... Okay, that's not the right problem. We don't do anything with square root. Okay. Yeah. Oh, and we gotta make it an integer. And we also really, really want to start with the number 1 and not the number 0, so let's do that. And this we'll just do a +1, just in case, because let's say we hit the number 25. The square root of 25 is 5. And range of 1 to 5 will not include the number 5, so it won't get counted. That's not great. So, +1. Okay, so for n in range, starting with 1 to the square root of the num, let's say if is factor in num, then if it is a factor, then it's evenly divisible. So we want to count plus equal to 2, I think. Not every time. So the reason I'm saying plus equals to 2 is because we're making this just slightly more efficient by only going to the square root. So, like, again, the case of 25, right? Evenly divisible by 1 and 25. 2, no, it's not evenly divisible by 2. It's not evenly divisible by 3. Okay, bad example. Let's look at the number of 28. Because, or honestly, let's even just look at 21. And you can kind of see what I'm saying here. So 21 has a square root that we're rounding to, gonna say 4. Because 4 times 4 is 16. So it's somewhere between 4 and 5. So we look at 1, it is a factor. Also, 21 is a factor. We look at 3, it is a factor. Also, 7 is a factor. These second two numbers are larger than the square root, and these first two are smaller, and we're only counting up to the square root, so every time we find a factor, it has a corresponding factor on the other end of the number. Up until we do hit the square root, but, let's see. So we want to have basically if num square root, and there is another way to do square roots in Python, this is just what I know, equals n, then count equals 1, else count plus equals 2. So if it is a number with a square root, and that square root is equal to the factor that we're looking at, then yes, we only want to count it one time, and that'll be the last one we count. Realistically, the number 25 isn't going in here, and there's probably not very many of these triangle numbers that are square roots. Or that have even square roots, I should say. Okay, so there's our little somewhat efficient counting of how many factors there are in a number. So down here, we're going to have our triangle num equals 1. And we don't really know how high we need to go. So we're going to do something that's a little bit risky and create an infinite loop. We will be adding a break statement, so it won't actually run infinitely, but sometimes creating an infinite loop is what you want to do. So triangle num equals 1, and let's go ahead and say I equals 1 as well. And or actually, let's start with I equals 2. And here's what we're gonna do. So if count factors of triangle num greater than 500, print triangle num and break. And obviously, we're gonna go through this loop quite a few times before we hit that. Like, I don't know how many times. It would almost be interesting to see. Let's actually see. Let's do that. Let's go ahead and make this a formatted string. Do that. Is the ith I'm trying to see if my math checks out. Not if I do it this way. So in this scenario, which is impossible, the triangle num would only have... If the triangle num right off had over 500 factors. And yeah, because of how English works, the th suffix is not always going to be right. But we're going to pretend, and maybe we'll get lucky and it is right. You never know. I have no idea what the number we're looking for is. So then we want to do I plus equals 1, only ever 1. And then triangle num plus equals I. So in this first case here, we come in with I. Obviously, we're going to not have 500 factors in the number 1. Or we come in with 1, 1. We're not going to have 500 factors because, duh. It's the number 1. So we say 1 plus equal to 1. 1 is I is now, or I plus equal to 1. I is now 2. Triangle num plus equals I. So 1 plus 2 is 3. We're now at 3. And let's, like I said, pretty naive approach. I'm very confident that it will actually find the answer, but again, the challenge on Project Euler is not can you find the answer, it's can you find the answer by writing a program that will run in under a minute. And let's see. And I'm actually going to run in a little trick that I've got here. I'm going to do factor count equals count factors triangle num, actually. Because I kind of wanted to display this too. I'm curious. Factor count. And it has factor count factors. Now, I think that we're very unlikely to have the factor count jump significantly, but just the same, I think I'm going to do this based on I. Basically, what I'm doing is I'm adding a print statement that kind of gives us some idea of what progress we're making. And in this case, I'm just going to do if I mod 100 equals 0, print checking triangle number. So just every 100 numbers, which let's just see how quickly it starts spitting that out. That might actually be a little bit more than we really want, but we'll see. Python problem 12. Yeah, that's spitting it out very, very, very quickly, as you can see. Okay. Cool. So that actually ran a lot faster than I expected it to. So it started at 4254 and some change, and it ended at 4259. So what I thought was an inefficient algorithm actually ran in a few seconds. Okay. Always better when you perform. Always nice to perform better than expected. I'm gonna have it only print out the thousands so that we have fewer lines here. We can more easily see. Okay, so importantly, we did get the exact same answer. So we've got this 765, 76500. Interesting pattern to that number. And that's a lot of numbers. So 43, 51.8, 43, 45.7. So 6 seconds again. And I only added this because I thought it would take longer to run, frankly. So I'm a little shocked. But let's see if our faster than expected algorithm actually gave us the correct answer, because that's the real test, right? It doesn't matter how efficient it is if it's wrong. At least that's my opinion. Awesome. So cool. We did get that correct. And if we go to the problems page, is there a little PDF? So I could call it here, but I'm curious if the PDF gives a more efficient algorithm. Without giving any second thought to the problem, it can be solved by brute force. Yep. This is saying exactly what my first thought was. It can be solved by brute force simply by generating the triangle numbers as described, dividing each by all the integers up to that triangle number, and counting those which are exact divisors. The answer is obtained when the count exceeds 500. So triangle number equals 1, the number to add equals 1, count is 0, while count less than or equal to 500. We're doing count equals 0 at the top to reset it, I assume. this is exactly what I did with I and triangle number. And then for every digit, we're doing the same if check and counting. So this is actually really, really similar to the algorithm that we did use, except they're going through all of the digits instead of going through the square root and being smart. However, as I expected, the above is extremely slow. It can be improved somewhat by halting divisions when the divisor exceeds the square root of the triangle number. That's just exactly what I just said. For every exact divisor up to the square root, there is a corresponding divisor above the square root, which, again, that's what I said. So, if... and then they just subtract 1 from the count if it's a perfect square, which is kind of neat. That's the other way to do it. And in though an improvement, the above is still very slow. Any integer n can be expressed as follows. Where p of n is a distinct prime number, and a of n is its exponent. For example, 28 equals 2 squared times 7 the first. So they're going into a very, again, very, very mathy approach. I'm sure this would be more efficient. The number of divisors of any integer can be computed from this exponents of their primes. For example, the number of divisors of 28 would thus be 2 plus 1 times 1 plus 1, which is 2. So 3 times 2 equals 6. Okay, so it's the exponent plus 1 times the exponent plus 1. Okay. A table of primes will be required to apply this relationship. The efficient preparation of a prime table is already covered in the overview for problem 7. Which we did go over. Since the largest expected triangle number is within a 32-bit integer, a table containing primes up to 65,500 would be more than sufficient. The following code assumes that this array of primes is already available. Okay, so here it's just sort of doing it by counting the prime factors, which definitely would be more efficient. However, unless you happen to know all of this math stuff, I think that the code would be more confusing. And obviously the goal is efficiency. And, like, let's go back to this algorithm. This magic number right here, if we made that 1,000 even, so double, our program is very unlikely now to run in, and let's go ahead and make this 10,000, anything like the same efficiency. So this will definitely take over a minute. Let's just kind of see. So in a few seconds it gets to the 10,000th triangle number, and then it'll gradually take longer and longer to get to the next one, which I could prove by outputting the timestamp on these. I probably should have done that. 20,000th. We'll leave that run while we keep looking at this. And the above can still be improved a lot by considering the fact that triangle numbers can also be obtained according to n times n minus 1 divided by 2. So the total number of divisors of t can thus be obtained according to this math formula. Okay. So, in other words, to find, say, the 1000th prime number, it would be 1000 times 1001 divided by 2. If I'm understanding that correctly. So then the total number of divisors for the 1000th prime number, or triangle number, sorry, would be D. Oh, and it's still, that still requires us to know the factors, okay. Interesting. So D of 500 times the D of 1001. Yeah, that is a neat mathematical trick there. Each component being much smaller than the triangle number itself, it would be much faster to determine the divisors of each, obviously. And the required table of primes will also be that much smaller and faster to prepare. Primes up to only 1000 will be more than adequate for this problem. In addition, the result of the n plus 1 component can be reused as that of the n component for the next triangle number without any need to compute it a second time. Yep, fair enough. Oof. So in assembly, including the generation of primes up to 1000 and almost fully optimized, it runs in less than 1 millisecond on a whatever that is. It should easily run in less than 10 milliseconds when written in most modern compiled languages. So, and it says you can safely start the computation with a prime much higher than 3. Valid. So yeah, there's definitely a more efficient way than our algorithm. Okay, so here. That actually did take just a little over a minute. And again, I'm kind of going to assume this is correct because the answer to the 500 one was correct. Oh, interesting. It has 1024 factors, which means the number before that had 1000 or fewer factors. Very intriguing to me. So obviously, we have built an algorithm that does not scale, once again. I'm not going to put in the other algorithm this time, but I enjoy learning about these different ways of doing things, especially with the rise of big data and just the sheer scale of what we need to do in real life programming nowadays. It is important to think about how can I make the most efficient algorithm possible. The algorithm that we wrote, obviously efficient enough for Python for the problem given. But it's not the most efficient algorithm, and it doesn't scale very well. I'd be willing to bet that the other algorithm scales a lot better. But yeah, I'm going to call it there for today, and I'll see y'all in the next one.